this is very well motivated, this problem of TQBF that we defined. It's coming from SAT, quantifiers, not just there exist, but a mix of there exist for all. But it's even nicer it's if we look at it as a game. Okay, if you think of there exist as yourself and for all as an opponent. So there exists a strategy such that for all the strategies of your opponent and so on. Okay, so let us formalize this as a game called the QBF game. So the truth of QBF psi, which has a there exists x1 for all x2, there exists x3 dot dot dot, there exists x. So the odd ones are they exist, even ones are for all. On phi x1 to x2n. So truth of this can be interpreted as a two-player game. Okay, so we'll see this as a two-player game. So think of there exist as you for all as your opponent. So you will pick x1, the x1, such that no matter what your opponent picks, which is x2, you will have a choice for x3, such that no matter what x4 is picked, you have an x5, okay, and so on, such that ultimately phi becomes true, which is the state where you win. Okay, so this is it's actually fixing a strategy for you so that you win the game in 2n rounds. Well, 2n steps or n rounds. Right? In a round, you move for take a step, your opponent takes a step, and then repeat. So say player 1 picks values for you can think of yourself as player 1. So your choices are by the odd variables, and player 2 picks values for even ones. So we declare player 1 the winner. There is only one winner, right? You don't want to have a tie, you want to win. So player 1 will be declared the winner if phi is true in the end. Right? So phi is the target value, and that has to be true if you want to win. So how should player 1 and player 2? How should player 1 choose such that without knowing player 2's strategy, player 1 always wins? Right? So the TQBF is essentially the problem of whether there is a winning strategy. So deciding whether psi is in TQBF signifies whether there exists a winning strategy for player 1. Right. So TQBF is the question of whether there is a winning strategy. So note that instead of talking about whether there is a satisfying assignment, where there is a true assignment, we are now talking about whether there is a winning strategy. Right. So from values we have moved to strategy level. So this is a much more general setting than NP hardness. And so this suggests the p-space hardness of general board games. I mean, board games are finite games, but if you make it growing, if you keep making your board, say, number of squares in a chessboard more and more, then the sequence of these problems, they become harder and harder, and in fact p-space hard. Okay, so this is what the above suggests. Example, chess on n by n board, Go on n by n board, checkers on n by n board, right. So we have not proved it, but this strongly suggests that these board games should be quite difficult, although proving this rigorously will require a lot of effort. This is just a suggestion. If you look at this, whether NP is different from p-space, so now we have a good, let's say, physical interpretation of this question in terms of games. So this question is saying that whether games are harder than puzzles. Right. So puzzles is what SAT signifies, because you have to find one assignment, true assignment, satisfying assignment. While games, you have to find the strategy, right? So it's at a higher level than just finding a satisfying assignment. So whether games are harder than puzzles, this is in computer science the question whether NP is different from p-space. This is an open question. So currently we don't know this. One more important consequence of this theorem of p-space completeness is that we can study NSpace using it. So in fact, let me just say lemma 2. So lemma 2 is a nice way, is a clever way to study NSpace. So what we will show is this theorem by Savage from 1970, that NSpace S can be simulated if you have, I mean, the non-determinism part can be removed. Non-deterministic bits can be eliminated in space S square. Okay, so let M be Sn space NDTM deciding language L which is in NSpace S. And note that this is not believed to be true for time. So, n time S, you will not expect it to be in time S square, you will expect it to be in 2 raised to S. But for space, why is this happening? Okay, why do we expect n space S to be simulable in quadratic space, in a quadratic blow up space? So, that is because in lemma 2 we gave we wrote the whole computation as a TQBF instance, and that TQBF you can actually solve in small space. Okay, that is the reason. Small space allows you to look for all the solutions. That is the idea. Write psi m comma x and solve it. Okay, that is what we will do. So, as in lemma 2, we design a QBF psi m comma x which is psi d Sn. Remember, we had this constant multiple of Sn, that much of space was being used, and so we bounded the number of steps to be 2 raised to ds, and then we looked at the midpoints and broke up by recursion, or designed formulas by recursion. So, path from start configuration to accept. But in lemma 2's proof, we used a deterministic Turing machine. But will it matter? So, you observe that it will actually not matter whether it is deterministic or non-deterministic Turing machine, because on the top there exists configuration quantifier, right. So, you just want Turing machine to have some path, that is all. So, the same proof actually works also for NDTM. So, with the modification, that phi mx cc prime captures two possible transitions. Instead of a unique one. Because now M is an NDTM, right. So, you just capture the existence of C prime prime in the middle, and yeah. So, in lemma 2 what was phi? Yeah. So, you just work with this transition C to C prime. Yeah, just work with transition C to C prime. But think of this as, express this as two possible transitions instead of a unique one given by the transition function, given by the transition function m, delta m. Okay, so that will still give you a formula of similar size. So you can observe that psi mx remains QBF of size big O of S square. And next you can actually solve it, which means you can check it in the same space as we saw before lemma 1. Right, lemma 1 we saw this algorithm which was linear time. So now by lemma 1 psi mx is checkable in space big O of Sn square. In fact, first we say linear in the size, which is then S of n square. Right. So this way we have shown that n space S is in space S square. So with the problem L has gone inside space S of n square. So any problem that is non-deterministic space S can be solved in space just quadratic. This quadratic blow up is coming from lemma 2, okay, not from lemma 1. Okay. So in particular, what did you learn? So you learn that NP space is equal to P space, right? Because NP space will just, the blow up in space will be only quadratic, and that is not going out of P space. Okay, it's still a polynomial. P space is the union over all the polynomials, so NP space immediately becomes equal to P space. So which is why for P space we will not talk about non-determinism. Okay, non-determinism does not help. Okay. There is another way to interpret what we did here in Savage's theorem, which is by looking at the tree of transitions over configurations. Okay, let's do that. So another way to interpret this is through the configurations tree of NDTM M. So configuration tree means that you look at this tree that starts with, at the root it has C start, and then there are two possible transitions. Let's call it C0, C1. C0 has another two possible transitions, 0 0 0 1. C1 has C1 0, C1 1, right, and then it expands like this. So that's the configurations tree. In the leaf of this tree, so the computation direction is top to bottom, right? That's how the computation is proceeding, but in every step there are two possible transitions because we are in NDTM. Otherwise it was just a line, but here it becomes a tree with the depth being, so depth is the number of step, the time complexity, which we have shown to be 2 raised to big O of s. This much time it will take, and each configuration has size also big O of s, right. So each configuration has size around s, and the total number of configurations is 2 raised to that, and 2 raised to OS is also the number of configurations in any path from root to the leaf, which is called depth. So specifying a location in the tree requires how much space? So you have to basically specify at what depth. In fact, you just have to specify this string, right? This 0 0 0 1 1 0 1 1. So that length is only log of the size, basically log of the size of this tree, which is log of 2 raised to big O of s, which is big O of s. So this much space, right? So you can specify any location in this tree in big O of s space, and then in that location how many bits are there? Size of a configuration is also big O of s, which altogether means that reachability of C start to C stop, start configuration to stop configuration, whether there is a path in this tree, right? That's a reachability question. This can be solved in how much space? In big O of s times s, which is big O of s square space, right? You can basically do a depth first search kind of an algorithm, and this tree is given to you only implicitly because it's exponentially large, but you can attempt this reachability algorithm that you know from graph theory, computational graph theory, and the space complexity of that will only be order of s square, because that is product of length of the path and times the space you have to maintain when you are at any vertex. Also, in 2 raised to big O of s space and 2 raised to big O of s time. You can also solve reachability alternately. You can basically work with the whole tree, which is of size 2 raised to big O of s, and in that much time you can solve it just by DFS, right? So there is also a space-time trade-off. Either you take space-time roughly equal, but then it becomes exponential, or you reduce the space a lot, which is only quadratic. But then time will blow up. So you can use this trade-off. So there is a trade-off that you can do. So these are the simple observations just looking at the tree and the reachability problem. And the reason why I gave this alternate interpretation is because we'll actually use it now in a new class that we'll study, which is the log space class. So reachability plays an important role in small classes like L, NL, etc. Okay, so in the next class we'll look at the structure of NL, non-deterministic log space, and we'll introduce the concept of NL completeness. Okay, so everything in NL will be doable in polynomial time because of this tree idea, right? Because if you take S to be log n, then 2 raised to s is just n. So everything can be done in polynomial time. So these are actually, this is why L and N are small classes. But still we can make comparisons and study the structure.